Welcome to Lesson 3, example number 1. And what it is asking for is for us to find the size of beam, considering bending stress only, using number 1 or better Douglas fir, and assuming that the weight of the beam is included in the dead load. And this is a pretty easy, straightforward problem. It looks like some of the things we need to remember is we have a 100-pound dead load, 100 PLF dead load, and a live load of less than 7 days duration of 1,000 pounds. And if you remember, if you read the section ahead, is you take a look, and for 7 days duration, live loads, you want to hit the capacity of additional 25%. And I'll show you how to do that real quick. But that's if we have live load, which we do. And I guess from the start, you should be able to say, hey, if I have just dead load, or if I have dead load and live load, is that going to be enough to compensate for it? You know what, that probably doesn't make a whole lot of sense what I'm trying to get across there. So we'll just work it out. So what we want to do is say, okay, well, if we just had the dead load, is it going to induce more stress than the dead load and the live load? Here it is. Is dead load at 100% capacity more than dead load plus live load at 125% capacity? Since we're going to be hitting that capacity at 1.25. So that's what we want to figure out. And I think right off the bat you can say, well, yeah, because you're doubling the load, but you're only increasing the capacity by 25%, but you're doing 200% of the load. So you should be able to tell right away. But we'll go ahead and work it on out. So if you remember, this is this distributed load on a simple span, and that M max equals WL squared over 8. And you could go ahead and, that's a little messy, let's clean it up. You go ahead and do moment diagrams, solve for the reactions, and do all that stuff. But when you have simple stuff like this, you can use these equations, which are always found in your AISC Steelbook or found in other analysis books and whatnot. You should be able to find them online. They are very, very, very commonly used. Anyways, let us move ahead. So we had mentioned before we want to find the moment of dead load, and we want to find the moment dead load plus live load. Alright, so let's begin. Dead load only. We have 100 PLF, pounds per linear foot, times your length, which is 22 foot, squared, over 8. Let's go ahead and calculate that out. 100 times 22 squared divided by 8 equals 6,050. And that is in foot-pounds. Alright, now we move down here. Actually, we can work out the stress later. Let's go ahead and we have 200. Add those both together. I put 100, I meant 200. PLF times 22 foot. And this should be double that, since that's linear. It should be linear related, since we're just multiplying it essentially by 2. It'll show over here, so 12,100 foot-pounds. Alright, so now we have the moment. But what we need to find is the section modulus. And the section modulus will give you the stress. And we'll work that back out once we can find the actual stress as opposed to the allowable stress. Now, right now we're going to look for the allowable stress because we want to pick our section modulus, and therefore we'll figure out what our section modulus min is, and then we'll pick the section modulus that is slightly greater than that, the most economical beam. So we've been given the fact that it's a number 1 or better. So we go to table 23-1-A-1, I think that is, and we go look at Douglas fir, and it says number 1 and better. Okay, we follow it over. Force and bending. Force and bending equals 1,150. and that's PSI. Alright, so that's what we have to work with. That is our force and bending, and I'm going to put a capital F, meaning this is allowable. When I say FB, I said force and bending, I mean stress and bending. I'll say that and I'll mess up. But every time you see an F, it means stress. I just see an F and think force. That's my, I don't know. Anyways, force and stress and bending is usually, this is your load, and this is more your capacity, is the way I like to look at it. So anyways, you have your stress and bending. Alright, and if you remember, stress and bending equals MC over I, or M over S, and we had looked at that in the last videos. So if we say, hey, this is our max, this is what you could say, hey, this is the maximum we can allow. This is kind of your allowable stress, I would call it. I'm going to write it over here. That's what they're going to allow. That's the max stress. So if we went in there, we would be able to find our min S, because we have that. Now, does that make sense? I hope so. But let's go ahead and write it out here. I'll switch colors. Alright, let's go ahead and solve using our max stress. And hopefully I can go back and show you what I mean. So we'll say the force, let's find the stress of this MDL, given that we're maxing out the stress. So we want to use this equation right here. And we'll say FB equals M over S. And that equals, we said FB equals, remember we're maxing out the stress. And then we have our moment. And this is dead load. Let's just do this right over here. Dead load only. And we wanted to say that was 6,050 foot-pounds over S, which is inches. I'll put it like that so we don't get confused. That 5. And that's in inches to the third. And when you say, well, we have foot up here, so we need to switch that to inches. So inches times pounds divided by inches cubed, we'll get rid of that and you'll be left with PSI, which is what we want. So we say 12 inches per foot. And that should get rid of foot and put in inches. You'll cross out that and cross out that. Alright, so let's back up here. So what I will call S min, and hopefully this you'll realize that this is the S min, meaning if you had something bigger, the S would be bigger, meaning this would be smaller, and therefore this would be less than the allowable stress if S was bigger. So we want to find the minimum S. This will actually not find, this will give us the minimum X. So let's go ahead and solve. We're going to bring S to this side, 1500 to this underneath, so it's 6050 divided by 1150. Oh, I forgot to times it by 12. And we get 63.1 inches cubed. Let's check that. Make sure we're on the right path. 63.1 inches cubed, we're right on. Alright, now we want to go to DL plus live load. Dead load plus live load. And remember, we have to mess with the S in this situation. So our force and bending equals our stress and bending, sorry. Alright. Which we want the max stress you can have is 1500. Your load equals foot-pounds. And you're going to hit that by 12 inches per foot to get it in the units you want. And you'll have S. Let's go down again. So your S min for dead load and live load equals, now remember this is, I still haven't factored it, and I'll show you this in a minute, equals 12 100 times 12 divided by 1150, 126, and hopefully that makes sense. 0.3 inches. That's about half, or this is half of that, so double it, and that makes sense because we doubled the load. Alright, so we have double load, we need double the beam, but remember, since we have this live load, that's only going to happen every so often. Every week, we said, well, you know what, we can increase, since it's not going to be there every single time. It's not an everyday load. It's only going to happen sometimes. The code book is saying that we can increase this, or increase this rather, by 1.25, or 125%. So let's go ahead and do that. And we do that, 1150 times 1.25, we get, let's switch colors here, this times this, and you get 1437.5 psi. And that's a little bit more intuitive about what they're allowing. And I know they didn't do that on, or maybe they did. Yeah, they did. But it might be not. Just showing it this way might be a little bit better to understand what exactly this 1.25 is doing. Saying, well, you know, we're not getting that live load all the time, so we can go ahead and increase this capacity by 1.25, multiplying. So let's go ahead and do that again. 100 times 12 divided by 1437.5. And our new answer is 101.0 inches to the third. And really what they did that in the example, in the study guide as I'll call it. They did that right away. They put it and kind of made an equation for S, which you could do that. If I always remember one form of the equation, this, and then solve as I need algebraically. But you can do it however you wish. So anyways, we have 101.0 inches to the cubes, or we have 63.1. And sometimes I'll do this. I'll box it, or you can just put a little controls. Since this required S-min is bigger than this S-min, this one is larger, and it will control, saying, hey, this S-min is greater, so we need to have greater than 101.0. So let's go to the other table, switch back, section properties of standard dressed sawn lumber. And we have 101 inches to the third. We go down 101, 102.4 is kind of right on the money. It's just slightly better, and that's a 4x14. A 4x14. So let's keep on going down and see if there's anything closer. 107.3. There's a 101.3, an 8x14, or a 4x14. I'm guessing that the 4x14 is cheaper. Am I looking at this wrong? Yes, I am. I was the section area. Never mind. Yeah, your 4x14 is going to be your most efficient section, which is 102.4. S equals 102.4 inches cubed. So let's go back and let's actually find the actual stress. We have a minute here. Let's see if we can do it quick. Okay, so we have 102.4. We had M. M equals 100. 12 over 1. S equals 102.4 inches cubed. This is foot-pounds. This is inch over foot. And that equals 1,000. Oh, we'll say that, 1418. And that is PSI. But remember, we hit it by 1.25, so let's divide it by 1.25. It should be right below 15, and it is. It's 1134 PSI. It's right below it. So we're good.